These are the solutions to question number 5 for the 2015 Chaos examination paper. So we want to plot a phase portrait and a bifurcation diagram for this planar system, and for part B we want to plot a bifurcation diagram for this polar system. So for part A, we first need to determine the number of critical points. So you can either solve this by hand or you can use MATLAB. You're just solving x dot equals 0, y dot equals 0. Straight away you can see that x is 0 from here, and from here we get y is 0, and we also have y is equal to plus or minus the square root of mu squared minus 1. So we have at most 3 critical points. The Jacobian is given by dp dx dp dy dq dx dq dy, which is given here. So you can see that there's one critical point if mod of mu is bigger than 1, and there are 3 critical points if the mod mu is less than 1. Okay, so if mod mu is bigger than 1, you can see that these two here will become imaginary numbers, so they disappear. So there's only one critical point if mod mu is bigger than 1, but there are 3 if the modulus of mu is less than 1. So we work out the Jacobian of each of the 3 critical points. For the origin, we just substitute x and y both 0. So here you can see that if mod mu is bigger than 1, then this will be a saddle point, and if mod mu is less than 1, then this will be a stable node. And here we have JB and JC, so these are the other critical points. And remember, there are only 3 if mod mu is less than 1, and if mod mu is less than 1 in both of these, then we get saddle points. So these are 2 saddle points. You easily sketch phase portraits. So for mod mu is bigger than 1, the phase portrait looks like this. And for mod mu is less than 1, here you can see there are 3 critical points. So those are your 3 critical points. And this is the bifurcation diagram. So you can see that the origin is always a critical point, but when mod mu is bigger than 1, the critical point is unstable because it's a saddle point. And when mod mu is less than 1, we have a stable node. So that's why this line here is solid, because it is a stable node when mod mu is less than 1. So this goes between -1 and 1. Now remember, we have 3 critical points when mod mu is less than 1. So these are given by this circle because we have mu squared plus y squared equals 1. So if you look at the y dot here, y dot is 0 when mu squared plus y squared is 1. So that's the equation of this circle. Mu squared plus y squared is 1. And away from the origin, both of these critical points are unstable, so this is a dashed circle. So here are your 3 critical points. The outer 2 are always unstable, and the inner one is stable. The bifurcation diagram for part B. So we have r dot is r times r squared minus mu squared. Theta dot is 1. So we have limit cycles. You can see here we have limit cycles when r is equal to plus or minus mu. And obviously the origin is also a critical point. So r dot is 0 when r is 0, or when r is plus or minus mu. Now for these cases, remember that r is always strictly positive. Okay, r cannot be negative. R is the radius to the limit cycle. So it's not difficult to show that the critical point at the origin is always stable. So that's a solid line there. And if you plot little phase portraits, you can easily show that both of these limit cycles will be unstable. So on the day of the examination, I would plot a little phase portrait on each side of this to show that the critical point of the origin is stable, and then there's an unstable limit cycle surrounding each of these. And you can determine that using dr by dt. When dr by dt is positive, you move away from the origin, and when dr by dt is negative, you move towards the origin. And there are plenty of examples given in the notes and the other solutions to the exams. And this concludes the solutions to question number 5.